When we track a projectile's arc, we map a specific geometric path through space. We use kinematics to measure the position, velocity, and acceleration along that path. But kinematics is purely descriptive. It only answers the question of how an object moves. To understand the physical reality of motion, we have to ask why that movement occurs. We need to identify the specific physical interactions required to pull an object off a straight line and bend its path toward the ground. For nearly 2,000 years, the answer to that question was dominated by a simple, intuitive observation. Because everyday objects like a sliding stone eventually come to a stop, Aristotle concluded that the natural state of all matter is rest. That conclusion was an illusion. Galileo and later Isaac Newton realized that unseen, continuous forces were acting on those objects. A sliding block doesn't stop because it seeks a state of rest. It stops because the force of friction acts against its motion. If you remove that friction, you reveal the law of inertia. Newton's first law states that an object in motion will remain in motion at a constant velocity in a straight line until a net external force compels it to change. Constant velocity, not rest, is the baseline of the universe. Force is not required to sustain an object's motion. It is only required to alter it. Once we recognize that forces cause changes in velocity, we need a way to calculate that change. Newton's second law, force equals mass times acceleration, acts as the mathematical bridge, translating physical pushes and pulls into predictable trajectories. This parabolic trajectory demonstrates the law. After launch, the only force acting is gravity's downward pull. Because force and acceleration are vectors, horizontal and vertical motions are independent. Gravity creates vertical acceleration, while horizontal acceleration remains zero, leaving forward velocity unchanged. Contrast this with uniform circular motion. Here, the force doesn't act downward, but toward a central point, perpendicular to the direction of travel. This continuous central pull changes the object's direction in every moment, without ever altering its speed. Whether the result is a parabola or a circle, the final trajectory is the geometrical result of the net forces acting upon the mass. Calculating that net force often leads to the cancellation trap. Newton's third law states that every action has an equal and opposite reaction. If every force is countered by an exact opposite, it might seem like no object could ever accelerate. When walking, your foot pushes backward, the action vector. In response, the ground pushes forward against your foot. These forces don't cancel because they act on different objects. Your acceleration is driven solely by the force acting on you, the ground's forward reaction. The cancellation trap is a boundary problem. If you do not clearly define the limits of your system, separating the person from the earth, you cannot accurately identify the forces that dictate motion. This principle of action and reaction pairs enables complex engineering, from simple springs to high-energy propulsion. In Panel C, the rocket is propelled not by pushing against air, but by violently expelling gas downward. The upward thrust is the reaction force to that expelled mass. These pairs also dictate how bodies interact during a collision. This diagram tracks momentum before, during, and after an impact. During impact, the internal forces are equal and opposite. Because they cancel out, the total momentum of the isolated system remains constant throughout. We see this in the math of a rifle firing a bullet. Starting from rest, the total momentum is zero. After firing, the massive rifle and the light bullet experience the exact same change in momentum, resulting in very different final velocities. These are the three pillars of dynamics. Inertia defines the baseline of motion. The second law bridges force to acceleration, and action-reaction pairs explain how momentum is exchanged within a system. Kinematics describes the map of an object's path, but dynamics explains the physical interactions that create it. Predicting how an object will move depends entirely on correctly defining the boundaries of the system you are analyzing.